So for this last session, I want to describe, as I said, the microscopic, something about the microscopic behavior of the Coulomb gas. And if you remember, we have started from a Gibbs measure and a free energy, and we've looked at the leading order that was telling us that the distribution of points resembles some equilibrium measure. And then we went to next order by introducing the next order energy, and we derived the next order term in the expansion of the free energy. And so today what we want to do is characterize this next order term also in terms of some observable, which is no longer the empirical measure, but something that's called the empirical field. Okay, so the empirical field. If you prefer, it's also a sort of point process. So this is the picture again. We have our point, and this is the support of the equilibrium measure. So this is size 1, and we want to take some reference point x, and we want to zoom around this point x. We want to zoom by multiplying by n to the 1 over d. And then we're going to get some configuration of points, which as n goes to infinity, extends all the way to infinity. So it's an infinite configuration. And the object is going to be, okay, so for each xn, we're going to define something. And let me call this map, I don't know. Again, I'm going to call it IN, maybe. So we're going to define something that at first looks a little strange, but so it's the average, or 1 over RD, the integral over B x. Okay, so I should be careful. So it's a cube. And 1 over dx radius r of the Dirac mass at the blown up configuration. So we're going to take the configuration xn prime. We're going to look at it in this ball. And we're going to translate it by xn to the 1 over d. No, by u du. So d u, and you want to take that. Okay, so what is this? We come with a little window. Okay, there's a window of size r. So in this scale here, this thing is of size r n minus 1 over d. Okay, so it's a possibly small window. When we zoom, it would be of size r. And we take the configuration. Ideally, we would want to just take the configuration centered at that point and blown up and put a Dirac mass. But for some reason, we have to average. So we have to move the centering point a little bit in this region, which is y the u. So we translate by u, and then we average over u. The reason is that in the end, we cannot prove a full LDP on the thing without the averaging. So the averaging is some sort of a technical point, if you want. So if you want, it's this thing is going to be called Pn, Pn xr of the configuration. So this thing is a probability measure because it's an average of Dirac masses. But it's still a random object, and that's the empirical field. Okay, so it's the averaged point configuration that you see when you zoom near X at this scale. Okay. So now what we want to do is we want to define some energy on infinite point configurations. So what kind of point configurations are we going to obtain in the limit? So remember, we have a potential that solves something like this. So now in blown up coordinates, it's something like that. Okay. Now if I take a n tends to infinity limit of this, at the limit I will have some function, probably this converges to something. So let's call it h. And here I'm going to have an infinite sum of Diracs. So let me call C this infinite point configuration. And then the mu prime, so mu prime is the blown up of the equilibrium measure. So it's mu, let's say mu v, x, n minus 1 over d. Sorry, it's mu prime. So this x is not the same as this x. Okay, so if you zoom near a point x like this, the equilibrium measure, if you assume it's continuous, it's almost constant, right, in a thing like this. So when you zoom, this thing is going to converge to just the mu v at x, which is this x here, the x that's here. Maybe I should call it x0. X0. This is x0. Okay, so we're gonna have some sort of PDE now in our whole space again, but with an infinite sum here and then a constant. So this becomes a constant just by the fact that you're blowing up something continuous. So when you blow up a continuous function, you just see a constant. In this thing, by the way, you're sort of losing the boundary condition. So when you solve this equation, you don't really know h completely. You know h up to a harmonic function. Because you're zooming, so you don't really know what the... Okay. And now we're going to define an energy, an infinite volume energy. So remember how before we had this thing, grad h n squared? Well, we're going to do the same, and now it's going to be for this h. So there is the w of gradient h is going to be defined as the limit as r goes to infinity. I'm going to integrate this over balls of radius r. And average, you know the notation with the dash, right? It's just the average. So you divide by the volume. And of course, this thing should be renormalized, but I'm not going to do it because this thing is infinite. Otherwise, you remove the, you smear the charges, etc. Okay, so for a given h that solves an equation of this form, we define that. And so this seems like a credible candidate because it has exactly a similar shape as what we were working with before, except now we have this thing that we take a box of size r, and we let it go to infinity, and then we divide by r. So this r, by the way, is not necessarily the same as this r. Could call it s. So what this does for you?
Do you have to subtract like kind of the mean, or like this should diverge? Or?
Okay, so you renormalize point-wise.
Okay.
Near each point because it diverges, so you have to renormalize, but otherwise, no.
Okay.
So imagine now you have this infinite point configuration, and you have a background which is uniform now. Right? So the background has become a uniform, so you can think of it as being 1. So a thing like that, physicists call a gelium. So that's why we call this a Jellium energy. So a Jellium is some sort of very toy model for matter where you have a uniform background charge and discrete opposite charges. Now, if you want to define an energy for a Jellium, which is Coulomb, in principle, you would have to sum pair interactions, right? You would have to sum the G of this point minus this point, and then the interaction with the background. But now you have an infinite setup, so it's not clear that such a sum can be made to converge. So somehow this thing replaces summing pair interactions. Okay, so now we define it at the level of grad H, but now we can define it at the level of a configuration. So this is for the potential, and this is for the configuration, which is here. And we're going to say, okay, it's the infimum over all things that solve minus Laplacian H equals this of the W like this. So because you don't really know what H is up to you only know it up to a harmonic function, you just decide to infimize over all the solutions of this. Okay, so this is the energy for configuration given the background density, which is M, which again you can normalize to be 1 if you want. Okay, so now this energy, it looks, the definition is a bit implicit, right? You have to take this int, you have to take that. What I claim is that it does generalize the pair interaction energies. In particular, for instance, in periodic cases, there is an explicit form in terms of pair interactions, which is of the form sum g xi minus xj. So it takes a form that would be more familiar, and g would be a Green's function of the torus. So what do I mean here? I mean here that I now restrict myself to configurations which are periodic in the sense that I take something in the torus and I just repeat it exactly. Or I take something, I repeat it exactly, which is equivalent to giving yourself a configuration on the torus, right? So this, my drawing is not very good, but it should be identical. Okay, so assume you have something that's periodically repeated, then this formula is equal to that. So then this equals that. So you recover a pair interaction potential, but for some sort of periodized Coulomb. So this thing solves this. One over the volume of the torus. Okay, so now this thing again also connects to the questions I was discussing in the first lecture, because we're gonna be interested in minimizing this function, and the claim is that, as I mentioned at the beginning, we showed with Mircea Petrache in particular that if the Kohn-Kumar conjecture is true, which it is in dimension 8 and 24, and it's still open dimension 2, then this lattices E8, respectively lambda 24, respectively A2, also give you the minimum of this W. And moreover, in all cases that's independent of this conjecture, for d equals 1, W is minimized at z. Right, at a configuration which, okay, so this is with the normalization of 1 point per unit volume. So you just put your points regularly. So in other words, W tells you something about the arrangement of points. It seems to prefer very regular arrangements. Okay, so in 1D, it prefers this periodic configuration. In 2D, we think it selects the triangular lattice. In 8 and 24, these lattices are optimal. In 2D, one thing that's known is that the triangular lattice is the best among lattices. Okay, so here this is a minimization over all configurations, all possible arrangements of points. They're completely free. Now, if you restrict yourself to the minimization within lattice, the lattice class, so you have the triangular lattice, you can make a square lattice or rectangular lattice. These are the choices you have. Then the triangular is the best. And this is a result from number theory. So, once you write things in this form, eventually you get into the world of number theory. So what this tells us, at least, is that this W can distinguish between different configurations. Okay, so G equals 2. Best lattice is triangular. And this is a number theory result from the 50s due to a lot of people, but Enola, Dyananda, Montgomery. Okay, so this thing is telling us something. Moreover, something we can show is that the minimum of W, you can approximate it by the minimum over periodic configurations with very large period. So if you don't want to work with the definition that I gave, you could work with this definition and make these boxes here very, very large. So if you let the size of the period become very large, eventually you get back to the minimum. You achieve the same minimum in the limit as W. And how do you prove that? In fact, it's by screening. Because screening is what allows you to copy paste, to cut and paste, in fact. Right? So imagine you had a configuration that's infinite, and somehow you knew it's optimal. It's achieved the minimum. Well, what you could do is you could cut a very large chunk of it. And the energy here would be almost the minimum. Screen it, and then once it's screened, you can just copy-paste it and bound the final energy by the sum of those guys. But since you're averaging for large volume, you're going to recover the same energy. So this is how you can show that you could restrict yourself to periodic things. Another little remark is that because of the definition, which got erased, but this definition is a large volume limit. You cannot expect uniqueness of a minimizer, because if you change points in a compact set, so now imagine you're going to infinity, but if you change just a finite number of points, this infinite volume limit doesn't change. So it's completely insensitive to compact perturbations. In the minimal energy problem that Kohn and Kumar phrased, you have the same problem, because they also define things as a large volume limit. And so if you change a finite number, you also don't change the energy. So you can't really talk about uniqueness of minimizers. It's not really possible. OK, so now what are we going to do with this quantity? How do we connect it to the original problem? So we're going to go back to the energy F. Right, and this is going to be rewritten after by the electric formulation as something like that, where this is my blown up electric potential. And this is the guy that's going to converge to, of course, this is to be renormalized, but this is the guy that's going to converge to some H that solves So in fact, the claim is that it's very easy to get a lower bound of this thing by the W. And the reason is it's basically Fubini and Fatou's lemma. Because you have an energy in some region like that, and you're going to come with a window of size R, and you're going to say, well, the energy in the whole thing is the same as the integral. When I center my box, I move it around, and I average the energy in the box. Right? So if you average the function in a box, and then if you average over the center, well, you recover the whole integral. There's nothing there, really. And then you can, so you're going to rewrite this as in the form of essentially of some average. So you see of over x and some average over b xr. So for fixed r, you can say something like that, and then you apply Fatou's lemma, and you're going to be able to say that the limit. So I'm skipping a little bit some steps, but again, it's all in the notes. Fatou's lemma is going to allow you to take the limit in here and re-express these things in terms of the Pn quantities that I was defining before. So these Pn quantities, they correspond to basically looking at the configuration in this ball and averaging it. So after a little bit of nonsense analysis, if you want, you get to the point that this is bigger than this function W of C mu V of x dPn x0, so R So here I still leave some n. So I want to rewrite things in terms of the W. Okay, I wanted to cheat, but I can't do that. This is not quite correct. I'm just going to take the limit straight away and write things in this form. Where Px is the limit of the Pn. Okay, so I have to erase here. Okay, so up to extraction, we assume there's some limit of this function, of this empirical field, right? So of course we would have to show that these things are tight, this Pn xr, that you can really extract a limit. The limit is a probability measure, and we call it Px. That is the that's the limit. And we're going to obtain a lower bound of this form. So now if you want to get the whole energy, you have to integrate this over all the centering, possible centering points. Okay. So now the claim is that this lower bound, which is essentially lower semi-continuity and tightness, nothing very deep. The idea is that this thing is sharp. So the lower bound is in fact sharp. And it's again by screening. So it's more or less what I was describing here. If you wanted to show that it's sharp, you had to take some infinite configuration. And you have to show that you can somehow take a piece of it that's of, you want to make a size n configuration in such a way that the energy at the level n, this energy, is less than that. So how you're going to do this is you're going to take your infinitely extended thing that has energy W. By definition of W, you're going to find some large size box where the energy in the box, so this is my S, right? You're going to find some S large enough such that the energy you find here, integral of grad h squared, is roughly equal to the W, because this thing is defined as some large limit. And once you have this thing, you screen it, make the boundary condition Neumann, and then you paste it with other things, so not quite the same, but you're going to, for each, you kind of split your region into squares, so you have the support of your equilibrium measure, you're going to split it into squares like that are microscopically very large, but macroscopically very small. And in each square, you can do as if mu v was approximately constant. And you're going to paste together different configurations obtained from taking this infinite almost minimizer and screening. So again, the advantage of the screening is that you can copy-paste. So not quite copy, but here, but paste, and glue together, and evaluate from above the thing. It's evaluated from above by the sum of these things of this form, right? Because the projection lemma tells you that if you have screened configurations, you can just add their energies, and that gives you a bound from above. So since you want to show this is sharp, a bound from above is what you need. And so it's basically provided by screening. Okay, so this is a part that requires a bit of work to make it precise, but it goes through. And so because the lower bound is sharp, the corollary is that if you wanted to minimize the energy, well, you started from the energy, you split, you extract the leading order, and you find that the next order you have to minimize f, right? So minimizers of Hn, which are the same as more or less minimizers of f, fn, xn, mu equilibrium. What are they going to do? Well, they're going to have to minimize this in the limit. So what do they have? Are such that their empirical fields, Pn, xr, and that's true for any r much bigger than the minimal scale, so let's say much bigger than 1 for simplicity. Here, much bigger than 1 is good. So they are such that this thing converges after extraction to P, and for almost every x, the px has to be concentrated on configurations that minimize W. So here there's this like measure probabilistic way that you have to phrase things, which is a bit annoying. But if you think about it, this is how this should. Okay, so Px, this is how you should say it, such that Px, almost every configuration, minimizes W. Okay, so I start from something that minimizes the Coulomb gas energy. I take a blow-up center. I look near X. I see in the limit an infinite point configuration. I have actually a law on infinite point configurations because I averaged a little bit. And okay, for almost every blow-up center, what I see is a minimizer of W. So we believe that in particular in dimensions 1, 8, 24, it means that you see a lattice. Okay. As I told you in the first day, in large dimensions, you don't expect a lattice. In dimensions 2, it's conjecture it's the triangular. In dimension 3, it's conjecture that it's one of the FCC or BCC lattices. So in low dimensions should be a lattice, but this is not known from the point of view of number theory. Not completely proven. But of course, this thing is, you need this sort of averaging because at the level of the energy, it could be that when you zoom, maybe there are some exceptional points where it's not a lattice, right? Sometimes you see there's some small regions where when you zoom, you see something else. Maybe you have a triangular lattice and another triangular lattice, and you rotate them, and you see a dislocation between the two lattices. So this would be a line where when you zoom, you see something else. I don't know. So all sorts of things could be possible, and they wouldn't really count in the limiting energy. So this is why you don't have a result that's an everywhere result, but only at this stage an almost everywhere result. Okay, so this is more or less what we can say about minimizers. And now I want to tell you something about states with temperature. So with temperature, it's not only about the energy. As we know now, with temperature, we have a competition between energy and entropy. So there's going to be an entropy thing coming up. And now this entropy has to be a relative entropy at the level of these empirical fields. So there is a Sanoff kind of theorem for empirical fields. If you want, the first question you have to ask yourself is, if I want to prove an LDP, which is what we do, what would the LDP be if there was no energy, if beta was 0, right? So if beta was 0, you're just then, your Gibbs measure, you can reduce it to something like that. If you remember, which is e to the minus beta, d mu theta tensor n times. So in other words, is there an LDP for mu tensor n times? You just throw your configurations IID with law mu, and you ask yourself what the blown up configurations look like. Okay, so forget about the interaction. So of course this question has been studied before, and it goes back to works of, in particular, Gheorghi and Zessin and others. And so you can phrase a Sanoff theorem. And what is the rate function? The rate function is something that's called the specific relative entropy. So we're going to call it specific relative entropy for a point process. And the only thing I care about is relative to the Poisson point process. It's defined as the limit. So it's again a large box limit of the integral. Actually, there's no integral. There's no integral. There's just 1 over RD. The usual entropy of the point process restricted to the box of size R relative to the Poisson point process restricted to the box of size R. Okay, so you restrict your thing in a ball. You look at the restrictions of the point processes. You take the usual entropy. You divide by the volume. You take the limit. So this is in statistical mechanics textbooks. For instance, in Friedli-Velenik, there's a nice presentation. Okay, so the Poisson point process, you've learned about it from Jean-Christophe. And here, what I have is a P. It's a probability on infinite point configurations. Okay, you ask also that these point configurations only give a finite mass to compact sets. So you have a finite number of points in any compact set. So it's called locally finite. Anyway, this is the kind of things we're going to get in the limit. Okay, so now we have a good candidate to be the entropy. And what is the LDP going to be? Well, there is a rate function, which is the sum of the energy plus 1 over beta times the entropy, right? That should be it. Okay, so let me erase here. Any questions on this? Okay, so now we go to the case with interaction, so beta is not 0. What should we expect? Well, we're going to define I beta rate function. Let me make sure I define it properly. So I beta m of p is defined as beta w. Okay, so this is integral of w of c m. So the m corresponds to the background intensity, but you can think of it like it's 1. Okay, so if you have a probability on infinite point configurations, P of C, you feed it point configurations, you compute the W of that point configuration, and you average. Okay, so it's the average energy right? Or if you prefer, it's the expectation of W under P. And then you put the relative entropy with respect to Poisson, or relative to Poisson. So this is the rate function that was introduced in a work with Thomas Leblay. And you see it has exactly the structure of a free energy, which is an energy plus 1 over beta. You could put instead of beta here, you could put it here as 1 over beta. An energy plus 1 over beta times an entropy. It's like a free energy. Okay, so before stating the theorem, we can already ask ourselves, what does this guy want? Right, so if you were to try to minimize this rate function, you see now you have a competition between energy and entropy, as always. And so the result of the competition depends on beta. By the way, you see how beta comes up here? This is the reason for the choice of having this n minus s over d in the temperature scaling here. It is chosen so that when you zoom, you see energy and entropy compete at the same order. So you really see an effect of temperature at the microscale. If you start to scale differently here, you would just lose one of the two terms. You would have either only the entropy or only the energy. So it would be a bit more trivial. So that's why it's kind of interesting to keep this scaling. But okay, so of course, so when beta is very large, that means temperature is very small. What you want to do is just minimize W. And this is how you expect that for very small temperature or very large beta, things crystallize, right? At least in low dimension. In those dimensions or in low dimension, probably other dimensions. And on the other end, if beta is much less than 1, then you can neglect the energy and you just want to minimize relative entropy. And you know that relative entropy is like is a form of distance, right? So to minimize the relative entropy, you can make it 0 if P is Poisson. So it's like convergence to a Poisson point process. Which again is not very surprising, because here you're just turning off the interaction. So if you turn off the interaction, the points are going to just be drawn in an IID way, and at the local limit level, you just see a Poisson point process. And so in between, you see you have this competition, and there's really a bit of order and a bit of disorder, right? You can think of this as wanting kind of disorder or independence, and of this as wanting order, and so this competition depends on temperature, and that's why in the simulations you see these things that are becoming more and more ordered at the microscopic level. Okay, so this one wants order, and this one wants disorder. Okay, so now I can state a theorem which is the gluing together of two theorems. I don't know if I'm going to manage to do it properly, but first it was proved by Leblay and myself at the macro scale level, and it also worked in all the Reese cases. Then it was proved by Armstrong and myself, also the micro, down to the micro scale level, but only for Coulomb. And again, it's this R, let's say, can go from being much bigger than 1 to macroscopic. And the theorem says something like the push forward of the Gibbs measure by this empirical field map. So I called it IN, or if you prefer, PNXR. So the push forward of that satisfies an LDP at speed r to the d with rate function okay, so there's two cases. If r is much smaller than 1, the rate function is I beta mu v of x naught minus its minimum. You always have to subtract the minimum. And if r is equal to, what did I say? N to the 1 over d, sorry. If r is n to the 1 over d, so then it's macroscopic, you have to average. So then it's the integral something like that. And that's the equilibrium measure. Oh, it's just that when you're at the macro scale, the density varies. So you have to let this thing vary. And when you're starting to zoom and look at mesoscales, then you can just freeze the density. And moreover, whenever you can prove a large deviations principle, usually you can also get an expansion of the free energy. It goes together with the proof. So moreover, you get an expansion for log z and beta. I'm not going to write the expansion because, okay, we know already what the leading order terms are. And what's interesting is the next order terms, the order n terms. And there are going to be, of course, so there's these terms, okay, theta n, e, theta of mu theta, for instance, plus beta n over 2d. Okay, so these are the leading order terms up to possible errors. But what's interesting is the order n term is going to give me the minimum of this thing. With a minus sign. Okay, so the free energy expansion is always giving you the minimum of the rate function here. And now what we can do is we can compare with the other expansion we had. And I will spare you the details of how you exactly compare, but what this is going to tell us gives the corollary that if you remember yesterday we had a function called fd of beta, which is the large volume limit of the free energy for a fixed background equal to 1 at temperature beta. And so the corollary is that beta fd of beta is equal to the mean of I1 beta. Okay, so over all p's that are stationary The reason why there's a beta is because here the beta was put in front. So when you compare, you get exactly this. All right, so yesterday, the f of beta was obtained as the limit as r goes to infinity of log k 1 cube r divided by cube r. And then we saw that once you scale things with the density that can vary, you get some integral of f of beta mu to the s over d. So there's some formula for the. But if you restrict to just uniform density equals to 1, it gives much simpler formula. And then you just get that. Okay, so what this does is it provides now what we call you can call a variational interpretation for this f of beta. Maybe let's keep this. So what we have obtained is a variational interpretation of f of beta. So if you remember, at the leading order, we have a coefficient here, right? And there's a variational interpretation for that, which is that this is the value of the minimum of E theta. And what the minimum wants is for the measure to look at, the empirical measure to look like the thermal equilibrium measure. And in the same way, at the next order, we have a coefficient, and this coefficient is the minimum of something. So this thing is the minimum of something, and this something, is some information about the underlying point process. Or sometimes you can also call it the local limit, because this is what you obtain when you take your system, you zoom at the macro scale, and you look at what happens. Okay, so now as another corollary, maybe, if you circle back to the beginning of the lectures, I talked to you about how there are some cases in which the limit point processes are known. So limit point processes are known. Okay, so there is the 1D log case. You have the sine beta point processes. Okay, 1D log case is not Coulomb. But in fact, this theorem, at least this part of the theorem, we proved it for all these Rees and log interactions. Okay, so this is okay for, in fact, for all of this range. And this is a sine beta point process. So what this is telling you is that the sine beta point process minimizing this guy. On the one hand, you have to minimize this, and on the other hand, you have to converge to sine beta. So the sine beta point process minimizes, and in the 2D Coulomb case, there is the beta equals 2 G libre point process. And so again, well, now what we can say is that the G libre point process minimizes this thing with beta equals 2. And let me point out that for beta different from 2 or D, that's general. So outside of these two cases, in the Coulomb case, the only thing we know, and this has been, there's a particular, I would say the best result now is a result of my former student Eric Thomas, shows the existence of a point process, but up to subsequences. So there could be multiple limits in some sense. But whatever limits there are, they minimize this thing. As a result, of course, we would be very happy if we could prove that this thing has a unique minimizer, because then it would characterize completely the limit. And unfortunately, we don't know how to prove that, except in dimension 1. So again, this 1D log situation is always somehow the easiest. So that was proved by Thomas Leblé with some co-authors. I think it's Erbar and Huisman. They proved that there's a unique minimizer by a sort of transport method. But other than dimension 1 log case, it's not necessarily expected that there's a unique minimizer, honestly, because there could be values of beta that correspond to phase transitions. And at phase transitions, you can lose the uniqueness of a point process, for instance. You could have several minimizers. There's another case where limit point processes are known. It's now d equals 1, s between, so all the Riesz cases on the circle. This was done by Jeanne Boursier. So she has existence of a sort of Riesz beta point process, but it's in 1D. Okay, so the corollary is that all these point processes minimize. Must minimize I. Okay, so the proof of this main large deviations principle, of course, involves the ingredients that we've already seen. You have to prove a lower bound, you have to prove an upper bound. It relies crucially, again, on the idea of screening. Right? So you want to take your domain, split into cubes, and sample kind of independently in these cubes. And it's the screening that allows you to do it. And then to sort of plug that together with this Sanoff type theorem. So it's a little bit tricky technically, but once you have the screening, you sort of have the core idea to manage to do it. Again, this idea that screening allows you to just glue together configurations and get upper bounds for the energy. So there's one direction, by the way, in the LDP, you always have two directions. One direction is easy. It's a direction where you can use the lower bound, right? I told you. So it's a bit like the discussion I had before. If you want to do it at the level of the energy, you have a lower bound. Once you have a lower bound, you can plug that into your Gibbs measure. It gives you easily an LDP upper bound, because you put a minus in front of the energy. So the LDP upper bound is just two lines once you know this and the Sanoff type theorem. But it's the lower bound that's difficult. And for the lower bound, again, you need to basically reverse this inequality. This is why you do it like that. You break up, screen, show that you're not losing too much volume, blah, blah, blah. Okay, so I'm trying to think if I have other things to tell you, but I think I'm pretty much got to where I wanted. I promised you a shorter session today, so I'm keeping my promise. But if you have any questions on this or on the topic in general, it's a good time. Yeah.
I don't know
Mm-hmm.
So even if there's not a unique minimizer, you can say that all the minimizers are Gibbs measures.
Mm-hmm. Mm-hmm.
Is there something similar here?
Okay, so I think this hasn't really been done, but I think if I understand correctly, what you're saying would refer to the possibility of defining also a Gibbs measure in infinite volume, right? So the closest thing is the work of De Reudre, Leblay, Hardy, Maeda, who did that in 1D, more or less by proving DLR equations. And so, as always, it's the difficulty is to show that you can sort of take care of the infinity. So I think that in 1D you can basically extract a result like that from their proof, but in higher D it hasn't been done yet, so something like that seems plausible.
So here consider the case of the distribution of the position. Curious if we consider the case of the distribution of the velocity, will it also satisfy some similar limit theorem?
Distribution of velocity?
Yes.
You mean in a dynamic context or what?
Yes, and here consider the positions of the particles.
Yeah.
But how about the case of the distribution of the velocities?
Oh, okay, so you want to make a Gibbs measure for non-equilibrium state, and you want to count velocities. You want to put velocities in there. I don't know. Never thought of that. Yeah, Chelin.
Yeah. So one result you have already erased in the middle. You mentioned the rate function for microscopic level and macroscopic level, and then you complete in macroscopic level. It is true for S between D minus 2 and D and for micros, and another result for microscopic level.
It's for Coulomb. Yeah.
That's only for Coulomb.
Yeah, it's just because at this stage it's only been proved for Coulomb. We're going to do it for Reese. It's in preparation, but it hasn't yet been finished.
But it's for every dimension.
Every dimension, Coulomb, any dimension, yeah. Eventually, these things are true for all the Coulomb and Reese cases that satisfy these conditions. Maybe I can mention one thing, which is for S bigger than D, we also have an LDP. And that's a quite different setup or situation. So for S bigger than D, there is an LDP, and this is in work of, in all dimensions, Hardin, Saf, Leblay, and myself. So S bigger than D is kind of funny because the interaction decays much faster. So it becomes effectively a bit like short range. And so screening then comes for free because when you have two boxes, you can put them together. They almost don't interact. So screening comes for free. There is no equilibrium measure because you can't even make sense of the potential theory problem. And so there is going to be an empirical measure limit, like a density, but that density is going to be determined by the rate function itself. So you have a similar rate function, and the rate function is going to basically involve both the local limits, the point processes, and the density. And when you optimize it, you find at the same time what the limiting density should be and what the point process should do, basically because these two effects happen at the same order in the energy. So the leading order of the energy, instead of being that you have, for us, we have N1 plus S over D, and we have something here, and then we have N, and we have F, right? In the hypersingular case, S bigger than D, everything is at N1 plus S over D. There is no other thing. So everything lies here, and in here you have both microscopic and macroscopic. And we also have a rate function. It looks a bit like that. But below D minus 2, strangely, nothing has been done. And below d minus 2, in some sense, again, the singularity is less strong, but the decay is less fast. So whether you having an equivalent of screening is not clear at all. Like whether you can sort of decouple the boxes. Another thing I could mention is that this thing gives the impression that somehow the boxes become independent. And in terms of the energy, it's not incorrect to think of them as becoming independent because you can add things, right? Things are almost additive. However, if you remember the CLT that we saw yesterday, when we take quantities like that, linear statistics like that, this thing's convergence to some Gaussian. And note that this is without normalization. So it's not like a CLT, usual CLT scaling, right? A usual CLT, you would divide by root n, and then you would have a limit. This is a limit without dividing. So these things are very non-IID in that sense. And so again, this is a strong manifestation of some type of much stronger rigidity than IID points. Anyway, I think I went far from the question, but if there are others, yeah.
Do you have an interpretation as to why you need to average when you look at the predicate?
So this is our technical limitation, is that we don't know how to just pick a point, zoom, because we use this sort of Fubini idea. We need to average. It would be much better to have a result that's non-averaged.
Yeah, because
would be more precise.
Theory, they do this without
Yes, but in fact, there are some things that they used to do with averaging first, right? Because they couldn't do it without, and then finally they got there. So the technology has to improve. No? Shall we get on the bus?